All right, so this question that we're working on is objects that are connected together. In this case, we have two sleds connected together. Sled 1 is being pulled and it's connected to sled 2 via a rope, and that object is also going to be pulled. Now, when you're doing any objects that are connected together, what you want to start off with is drawing a free body diagram. So that's what we're going to do for sled 1 and sled 2. So we're going to draw a free body diagram for both of these. Now, on both of these objects, there's going to be a gravitational force that is acting downwards and also a normal force that is going to be acting upwards. So we're going to label these. You can label these as FG1 and FG2. To be specific, you can also do that for normal force as well. That just makes it a little bit easier so that you know which masses that you're going to be using. Now, sled 1 is pulled. There's an applied force of 150 newtons to the east. So we're going to draw another applied force over here. We're going to label that F applied. When doing these type of questions, you want to try to denote which way is going to be positive and which way is going to be negative. So just to make it easier, we usually just do positive X to the right, and we can just do positive Y upwards, and east as well, or because since we have the direction east, we can just say that is our positive X. Now, we also have a rope between the two objects, so there is going to be a tension force this way for sled 2, and for sled 1, because it's pulling sled 2, it's going to be in the opposite direction. So we're going to label these as FT. Now, we don't need to say FT1 or FT2 because it's the same rope that is there. So the tension force between these two is going to be the exact same. So there's going to be no difference over here for those two. Now, this question is unique compared to chapter 3 is because there is kinetic friction that is present in these case scenarios. So for both sleds, there is going to be a kinetic friction that is going to be going in the opposite direction. So there's going to be opposite direction of motion. So we're going to label these as F kinetic. And again, we don't have to label them as 1 or 2 because both of them experience the coefficient of friction of 0.20. It's not like they're on different surfaces, they're on the same surface of ice. Now, what you want to do is that you want to do this as a system. So as a system, you want to combine these two, and we're going to combine objects. So both sleds combine. We're going to draw a free body diagram of both of these combined together. So imagine that they're one mass. So obviously gravity is going to be acting downwards. There's going to be normal force up. So we're going to call this Fg total. We're going to call this normal force. There is an applied force on both sleds because if you pull sled 1, sled 2 is automatically going to be pulled at the same acceleration. So this is going to be applied force in this direction. And the force that is going to be opposing this motion is going to be kinetic friction. So we're going to label it as this. Now, as you can see in this F free body diagram, we're ignoring the tension that's just connecting the two objects together. This is just both sleds combined. So what we do as both sleds combine moving forward, we're going to calculate the acceleration of the sleds as a system. So we're going to combine both of them and we're going to calculate this as a system. Now, in order to do this, we need our net force formula. So F net equals to mass times acceleration. Now, we have our applied force in our positive direction, and what's opposing it is our kinetic friction. So we're going to subtract that. And this is going to be mass total, the combination of the two sleds. So it's going to be mass 1 plus mass 2 multiplied by acceleration. And over here, we have our applied force, which we know, which is 150 newtons. So we're going to say 150 minus our kinetic friction. So we don't know that yet, so we need to figure out what kinetic friction is. Equals to mass 1. Let's see what mass 1's weight is. 18 kilograms. Mass 2 is 12. So it's going to be 18 plus 12 multiplied by the acceleration. Now, the thing that we're missing over here is kinetic friction. So in order to calculate kinetic friction, it's going to be mu k times normal force. And we know that normal force is equal to mass times gravity. Now, over here, because we're doing it as a system, you have to combine mass 1 plus mass 2. You're not just going to do it for one specific sled, you're going to do it for both of them combined. So kinetic friction for both of these, the coefficient of friction is 0.20, mass 1 is 18, mass 2 is 12, multiplied by 9.8. So the kinetic friction that we get over here is going to be 58.8 newtons. And this is going to be going in the west direction, as denoted over here. Sorry. Now, this kinetic friction is for both of them combined, so we can label this as total. It will make it easier down the road when we're doing any other calculations. So this is going to be the total kinetic friction of both of the sleds. So now, since we have the number, we're going to plug it in. So 150 minus 58.8 equals to 30 times acceleration. Therefore, we have 91.2 divided by 30 equals to acceleration, and our acceleration is equal to 3.04. Keeping with the significant digits, we have two significant digits, so we're going to round it. So 3.0 meters per second squared, and the applied force is in our east direction, or that is our direction of motion, so the acceleration also will have to be east. So now we have our acceleration. We can move on to the next part, which is calculating the tension in the ropes between the sleds. Now, what you can do is that because we're trying to find this tension force, it doesn't matter which sled you use. You can either use sled 2 or sled 1. My suggestion or my tip is to use the free body diagram with the least amount of forces so that it's easier to calculate and makes it a lot faster. Obviously, sled 2 has less forces, so that's the one I'm going to be showing you. So using free body diagram of sled 2, we have F net equals to mass of sled 2 times the acceleration. So we have our tension force to the right minus our kinetic friction, but this is kinetic friction only on sled 2. We're not looking at it as a system, we're looking at individual sleds now, which equals to mass 2 times acceleration. So our tension force, we can take kinetic friction to the other side. So our tension force is equal to mass 2 times acceleration plus our kinetic friction. So we can do our calculation now, or we can even go further. Our tension force equals to mass 2 times acceleration plus, in order to calculate kinetic friction, it's going to be mu k times normal force. Normal force is equal to mg. So we're looking at mass of sled 2, so it's going to be m2 times g. Now it's just a matter of plugging in our numbers. So our mass 2 is equal to 12 multiplied by our acceleration that we got from our previous question. Now don't use the rounded value or our value of significant digits. Try to use as many decimal places as possible. So we're going to be using 3.04 plus mu k, which is equal to 0.20 times mass 2, 12, times gravity, 9.8. So we get a tension force which is equal to 60 newtons. And over here, it is a force. Forces do have direction, but because this is a tension force, there is going to be no direction, because on tension forces, it's on the entire rope or the entire string. So there is no specific area where you're applying the direction. Now you can do the same thing using the free body diagram of sled 1, which I'll show you here, and you'll end up getting the same answer. So let's do a free body diagram of sled 1. So F net force is equal to mass times acceleration. Our net force for sled 1 is F applied, which is to the right, minus our tension force minus our kinetic friction of 1, which is equal to mass of sled 1 times the acceleration. So we can see over here now there's an additional two forces that we have to account for, versus on sled 1 there was only one force in going backwards. So over here we have to account for both of the forces. So our applied force we have is going to be 150 minus our tension force minus our kinetic friction, which is mu times mass of 1 times gravity. So we can fill all those values in. So it's 0.20 multiplied by 18.0 multiplied by gravity, which is 9.8, equals to mass of 1, which is 18 kilograms, multiplied by acceleration, which is 3.04. I'm going to skip a few steps here, but if you were to rearrange and calculate, you would get your tension force to be also 60 newtons. Now, do you need to do both of these steps over here for sled 1 and sled 2? No, you can use either scenario and both of them should give you the same, or will give you the same answer. You can use it to do a check just to see if you're getting the same answer or not. Thank you.